Assalamu alaikum. So today I will speak with you about how to select the IDSE, the reference current of the flux component of the stator current. Recall that if we are using either a PI current controller plus pulse width modulation, we need the IDSE reference and the IQSE reference. The IQSE reference actually is the result from the PI current control TE reference. If we divide it over the factor multiplied by IDSE, we are getting the IQSE. So even though we need the stator component of the flux in order to calculate the torque component of the stator current. Also, this is the case if we are using the hysteresis current control. In order to build the references, the current references, we need the IQS reference and IDS reference. And today I will speak with you how to specify or how to design the flux component of the stator current. The flux component of the stator current. And for that, I will start with a simple example. Let's assume that we have 400 volt, 50 hertz, 1370 RPM, Y connected, squirrel cage induction motor, has the following parameters referred to the stator circuit. RS equal to ohm, R dash equal to 5 ohm, XLS equal to XLR dash equal to 5 ohm, and XM equal 80 ohm. Now recall, those reactants are calculated at 50 hertz frequency, at the rated frequency. Now we need to find the IDS star. How we can do that? Now recall, in the rotor field-oriented vector control, we are ending up with the following relation of the slip speed, omega slip equal to 1 over tau r, IQ SE over ID SE. So simply, if we can calculate omega slip at rate condition, we are getting the first equation which relate the IDSE with IQSE. And here we have two unknowns, which is the torque component of the stator current, IQSE, and the flux component of the stator current, which is the IDSE. So we need the second equation. So the second equation from where? Now, do you remember the balanced steady state phasor relation? Now from the balanced state phasor relation, we are getting that square root of 2 IS as a phasor will equal to IQSE minus JIDSE. So simply from here, if we are taking the magnitude, we are getting that 2 is squared equal to iqse squared plus idse squared, and this is the second equation, and this is the first equation. So simply we need to calculate the stator current at rated condition. To do so, let's recall the per phase equivalent circuit. This is the RS, XLS, XM, XLR dash, and simply here we have the RR dash over S. This will be the XLR dash, XLS, RS, and this is the XM. And this is the VS, which equal 400 over square root of 3, because we are having a Y connected square cage induction machine. So B phase will equal V line to line over square root of 3. And we know that given this will equal 2 ohm, this will equal 5 ohm, this will equal 5 ohm, this will equal 80 ohm, J here, and J here, and this will equal 5 over S. So to calculate this resistance, we need to calculate the slip. The slip equal NS minus NR over NS, which will equal 1500 minus the rated speed is given 1370 over 1500. If we do the math, this will equal to 0.0866. So now we can calculate this value. 5 over 0.866, this will equal to 7.7 ohm. Now simply we have a simple circuit consists of two impedance in parallel with one impedance in series. So this will be 2 plus J 5 ohm. This will be the J80. This will be the 7.7 plus J 5 ohm. So now we can calculate here Z total, which will equal to 2 plus J5 plus J80 parallel with 7.7 plus J5. And if we do the math, here we are getting Z total equal to 36.98 plus J33.45. This is in rectangular form. In plural form, this will equal 49.864 with angle 42.13 ohm. Now we can calculate IS, which equal VS over Z total, and this will equal 400 over square root of 3 over 49.864 with angle 42.13, and this will equal to 4.63 with angle minus 42.13. ampere. Minus 42.13. Now remember, this is the RMS value. So IS as a maximum value will equal square root of 2 IS RMS value, which will equal to 4.63 multiplied by square root of 2. This equals 6.549 ampere. So now we're having the stator current, the maximum value of the stator current, and we can calculate here omega slip, which equal S omega S, and this equal to 0.0866 multiplied by omega S, which is the 2 pi F, and F is 50 hertz. So this will equal 0.0866 multiplied by 2 pi multiplied by 50, and this will equal to 27.226 rad. Now we know that omega slip is equal to 1 over tau r IQ SE over ID SE. So we need also to calculate the time constant of the rotor circuit. So tau r is equal to LR over RR, and this will equal to LR plus LM over RR. Now if we multiply here by omega E and here by omega E, we are getting the XLR dash plus XM over omega E RR dash. So XLR, we have it. This is the 5 ohm, and this is the 80 ohm, and omega E we know it, and RR dash we know it. It is the 5. So tau R will equal 85 over 5 multiplied by 2 pi multiplied by 50, and if we calculate that, this will equal 0.0541 second. So now also we can calculate omega slip, and this is the omega slip actually. So now we have 27.226 equal 1 over 0.541. Now instead of the IQSE, I will use the IDSE. Now we have the square root of 2 IAS was equal to, this is the IAS max, let's say, this equal to IQSE minus JIDSE. So IAS max square will equal to IQS square plus IDS square. So if I solve this one with respect to IQS, I will get the IQSE equal to square root of IAS max square minus IDSE square. So now I will substitute this one in here. So this will be the square root of IAS max square minus IDSE squared over IDSE. So this will be the first equation. Now, if we need to solve it, I will rewrite it here. So we end up with 27.226 equal to 1 over 0.0541. Here we have the square root of the IS max square minus IDSE squared over IDSE. Now if we need to solve this one, I will multiply here and square. So this will be the 0.0541 multiplied by 27.226 squared equal to IS max squared minus IDSE squared over IDSE squared. Now the IS max squared will equal, we calculate I think this one, 6.549. So this will be the 6.549 squared, and this will equal to 42.889. And if we calculate this one here, this will equal to 2.1615. If I multiply this one here, IDSE squared equal to 42.889 minus IDSE squared. Now separate the variable. This will be 3.1615 IDSE squared equal to 42.889. So IDSE will equal the square root of 42.889 over 3.1615, and this will equal 3.683 ampere. So this is the flux component of the stator current at rated condition. So this is the flux component of the stator current at rated condition. So simply, if we are controlling the speed below the rated speed, we need to keep the flux component of the stator current at its rated condition, and this will indicate that the flux on the gap will be constant. So